Great. Hello, everybody. Welcome to StreamLink, real-time data ingestion at OpenAI scale. Real quick intro. My name's Adam. I'm an engineer at OpenAI on the real-time infrastructure team. I'm actually the tech lead for the real-time infrastructure team. My team supports all kinds of streaming infrastructure across the entire stack at OpenAI, including Kafka, Flink, and other various streaming platforms. Previously at OpenAI, I worked at Stripe as the tech lead for the data movement team. So let's get right into it. I'm going to first talk a little bit about stream processing as it exists today at OpenAI. So again, we're very heavy users of Apache Kafka, Apache Flink, and also K8s, our in-house managed framework for Kafka consumers. In terms of our scale and adoption, we have more than 4,300 distinct Kafka topics. Today, we support a throughput of up to 60 gigabytes per second, or 10 million QPS. And my team supports, at this time, 12 distinct Kafka clusters. On the consumer side, we actually support 60 different production Flink applications and 120 plus managed Kafka consumers on K8s. Broadly speaking, we have a huge number of use cases, and really our use cases span across the entire applied stack at OpenAI. But today, what I want to talk about specifically is one facet of our general streaming platform, and that's our streaming ingestion. And when I say streaming ingestion, what I really mean is a service to get data out of Kafka into the data warehouse in incremental data warehouse datasets in near real time. And you might reasonably ask, what is so interesting about streaming ingestion that I feel the need to give you a whole talk about it? But really, for us at OpenAI, this is one of the most important components of our overall platform. It's actually the single most common use case for Kafka in general at OpenAI is simply as a way to ship data into our data warehouse. Our users tend to be very performance and reliability sensitive. If our data starts lagging or if our data sets go down, people tend to notice and they tend not to be very happy. And in our experience, with this kind of platform, there's a severe risk of operational burden if you don't build it and manage it correctly. And really, we're operating here at massive scale. Today, OpenAI's streaming ingestion platform has 1,900 or more data sets. And at this scale, operations can turn into a serious challenge. And in terms of our use cases, streaming ingestion supports product analytics, including the dashboards that go all the way up to our top-level C-suite executives. We also use streaming ingestion for training data collection, safety integrity enforcement, keeping our users and our platform safe, and many other critical use cases for running the business at OpenAI. And so all this to say that streaming ingestion is a really important capability for our platform. I'll talk briefly about some of the prior art, the systems that existed historically at OpenAI, just to motivate the development that we'll discuss later in the talk. So we have a legacy streaming ingestion platform based on Apache Spark, specifically Spark Structured Streaming, and orchestrated via Apache Airflow, which, for anybody not familiar, is a general-purpose data orchestration framework. This is sort of a high-level architecture for our legacy platform. We have configuration checked into our monorepo, generally authored and managed by our internal user teams. This configuration is projected into prod, and every individual configuration entry results in the creation of an individual Airflow task. This Airflow task, in turn, spawns and manages a Spark Structured Streaming application, which in turn is responsible for shipping data out of Kafka into our output tables. The core implementation here is honestly quite simple. Really, it's just a read and a write. We're just moving data from one place to another. But yeah, this is how things look at a high level on our legacy system. One quick note here, OpenAI today uses Delta Lake for our data storage in our data warehouse. This isn't super important for the purposes of the talk. This won't change over the duration of the talk, but just FYI, this is the tech stack in which we're building on the data warehouse side. So I'll talk about a few specific challenges on our legacy platform to motivate some of the improvements that we've invested in. One big issue that we've experienced is load spikes due to the Spark Structured Streaming microbatch model. So in contrast to something like Flink, Spark Structured Streaming operates on a microbatch basis, which basically means that it's just a recurring batch job running every few minutes. And so how this plays out for us is that our Kafka clusters tend to sit relatively idle for minutes at a time, but then all at once, our ingestion jobs will read hundreds of gigabytes from Kafka with very high parallelism. This is really hard to support and troublesome for overall reliability and latency characteristics. In the same vein, we also observe really poor resource utilization on our legacy platform. This is actually a graph of our CPU utilization over a 1-hour interval on one of our legacy jobs, and we see this very sharp pattern of extremely high utilization followed by periods of total idleness. And what this graph really says is we are wasting money. Broadly speaking, we see unstable performance for our largest data sets on the legacy platform. This is just latency over time for a notable troublesome data set. Sometimes it just lags. We don't really know why. And most importantly, this legacy platform has proven to be very operationally burdensome, both for real-time infrastructure and for our user teams. And yeah, pictured here is a real-time infrastructure engineer in the midst of their on-call shift with 1 million broken data sets. So yeah, all these challenges motivated us to ask the question, is it possible for us to actually do better? Can we build a better system? And with that, I'd like to introduce StreamLink, the subject of today's talk, OpenAI's next-generation data ingestion platform. So we had a few specific goals when we built out StreamLink. Most importantly, we wanted to improve overall stability and performance. We wanted to make sure that we could reliably ship data into the data warehouse with the lowest possible latency. We also wanted to reduce the operational burden and the total cost of ownership to OpenAI, both for real-time infra and for our user teams. And finally, as I alluded to earlier, we really wanted to mitigate that big spiky load problem on our Kafka clusters. So the single biggest requirement of StreamLink as a platform was actually compatibility with the legacy system. We wanted total feature parity in terms of the knobs that users could spin. We wanted to make sure that our output schemas were identical and that we supported the same serialization and that there was no difference in data quality between the two systems. And of course, we wanted to maintain equal or better cost and latency. And I'll get into this in more detail in the talk, but really the reason that we were so focused on compatibility was so that we actually had a trajectory to kill the legacy system. So here again is a high-level architecture for the new StreamLink platform. Again, we have configuration, which is just checked into our monorepo and authored by our user teams. We have a system called the StreamLink Watchdog, which I'll explain in more detail in a few minutes, which is responsible for creating and managing our StreamLink Flink applications. At the core, StreamLink is basically just a very simple Flink application that, again, reads data from Kafka, puts it in Delta. There's really not all that much intrinsic complexity to it. And yeah, for the StreamLink application, again, it's a very simple application using the Flink table API specifically. And so we lean on the open source Flink Kafka table source to read data from Kafka. We do some very basic internal SQL transformations and filtering just to get the data in the right shape for our output tables. And finally, we pipe that data through to the open source Flink Delta sync to get it into our data warehouse. So apologies for the very big screenshot. This is basically a view of the Flink web UI for one of our StreamLink Flink applications. And you see we have many independent data flows here. Each data flow actually corresponds to one individual Kafka cluster. OpenAI runs many Kafka clusters for availability and disaster recovery reasons. And so that's why we have so much stuff going on in this diagram. Zooming in a bit more closely, though, this is the data flow for one specific Kafka cluster. We see in this upper operator here, we actually have several fused operations as an optimization that Flink does internally. We have the Kafka table source, which is basically reading data from Kafka and deserializing it into Flink's internal representation. Again, we have our SQL select and filter operations munging the data into the correct shape. And then we have the first two phases of the Delta sync, the writer, which actually converts individual rows into Parquet, and the committer, which uploads Parquet to blob storage. Downstream in this lower vertex here, we have the Delta table sync global committer, which is responsible for committing the committed data files to our Delta Lake metadata on every Flink checkpoint. We basically lean on the Flink checkpoint process to persist our data durably and to achieve an exactly once guarantee with respect to the data flowing through Kafka. And to reiterate, this is a flow for one Kafka cluster. Depending on the specific topic, this is actually repeated 3 to 6 times in any given StreamLink application. So I'd like to talk a little bit about one specific challenging technical problem we faced on StreamLink. And that's the problem of partition release. So going back to our general user story for streaming ingestion, one of the most important use cases here is actually running batch data jobs downstream of these streaming ingestion datasets. But the problem that we face here, so StreamLink is writing out these hourly partition incremental datasets, and our downstream jobs run incrementally every hour, reading 1 hour's worth of data. But how do we actually know when it's safe to run a downstream job? Or to put it differently, how does a downstream job know when the data is actually complete? This is a very important question, because if we erroneously trigger downstream jobs prematurely, they will see incomplete data, and that'll propagate all the way through our data warehouse. On the flip side, if we wait too long to actually trigger our downstream jobs, that's latency. That's a latency penalty paid by every single use case in the data warehouse. And so really our problem here is to trigger downstream jobs as soon as possible when data is complete, but no sooner. So here's just a diagram illustrating the general shape of problem here. We have several partitions. Some of them are complete. Some of them are pending. The downstream job does not actually know which ones are safe to read and when it's safe to actually run. So our general solution here was to lean on Flink watermarks. So setting some context, Flink has a notion of event time, which is basically a timestamp for individual events independently of when Flink is processing the specific event. And a watermark is basically a marker indicating we have seen all data up until some specific event time. And on StreamLink, we actually use Kafka broker timestamps at the message level for our event time. And we infer watermarks based on the latest observed timestamp on any given Kafka partition, plus a few minutes of padding to account for any clock skew or out-of-order data. So having established our Flink watermark, our general strategy here is to propagate that Flink watermark into the output delta table in the commit metadata. And subsequently, we have an out-of-band process that pulls the delta metadata and marks individual partitions as released based on the completion signal from the watermark. Walking through that a little bit more visually here, we have Kafka and we have StreamLink reading from Kafka. Based on the progress on the Kafka topic, StreamLink actually knows, OK, my current watermark here is 1301. We've just ticked over the hour boundary past hour 13. We propagate that metadata into the StreamLink dataset as part of a delta commit. And the partition releaser, again, which is an out-of-band process, pulls the delta commit. And based on this watermark signal, we know, OK, the partition spanning from T12 through T13, that is now complete. We can mark it as complete in what I'm calling the partition marker store. At OpenAI, we actually just use blob storage for the partition marker store. You'll often find in other companies, you'll see things like Hive Metastore for this purpose. But it really doesn't matter. Any KV store kind of works here. Now, thinking how to integrate that with our actual downstream workloads, we introduce an Airflow partition sensor. And so the sensor, basically, it's an Airflow task that does not complete until a specific partition is released. Its sole purpose is to block until the partition is released. And then, in turn, our downstream jobs block in those sensors. Walking through that in a bit more detail, here we have a case where we have partition T12, which has been released by our partition releaser. This Airflow partition sensor sees this marker and unblocks the downstream job, which is therefore permitted to read the complete partition for T12 from the underlying dataset. Conversely, for T13, that partition is not complete. And you can see that StreamLink may still be writing data to that partition. And in this case, the Airflow partition sensor will block and will prevent the downstream job from running, thereby eliminating the risk of reading incomplete data. So this is all very cool. We have the core implementation of our Flink application, and it seems like it's going to work great. But we have a big challenge here of how do we actually deploy it? How do we get it running in production? And so to answer that question, I want to take a brief detour through the history of Kubernetes at OpenAI. So at OpenAI, basically all of our services are running in Kubernetes. We run hundreds of different Kubernetes clusters. And we actually have a lot of sophisticated tooling around Kubernetes and a centralized compute team, which gives us a great deal of support when running workloads in Kubernetes and managing those clusters. And so with all of that context, we kind of asked ourselves, should we run bespoke clusters for Flink? Should we build Flink clusters on top of raw VMs or on Yarn or anything like that? Of course not. We absolutely don't want to reinvent the wheel here. We actually want to use as much prior art and existing expertise in the organization as possible. And so with that in mind, I'll briefly introduce the Flink Kubernetes Operator. So the Flink Kubernetes Operator is basically a way of deploying and managing Flink applications on Kubernetes. It revolves around the Flink deployment Kubernetes custom resource definition. And so the Flink deployment CRD basically is a Kubernetes resource that represents a running Flink cluster and an associated Flink application. And it's the operator's responsibility to provision task manager and job manager Flink deployments based on the configuration in the Flink deployment resource. And overall, the operator is responsible for managing the application lifestyle based on the CRD. Looking at this from a more visual perspective, in this example, we could imagine using kube control apply to create a Flink deployment CRD in our Kubernetes cluster. The Flink Kubernetes operator, in turn, is watching for changes in the set of Flink deployment CRDs and creating or deleting resources via the Kubernetes API server to enact the configuration given by the Flink deployment CRD. And on the right here, we have our actual Flink cluster. Mostly, this is a task manager and a job manager deployment, plus some other miscellaneous resources. So having set the context about the Flink deployment CRD and the Flink Kubernetes operator, let me talk more specifically about one of our biggest challenges on our legacy platform, specifically tuning. In general, like I said, we have an enormous number of data sets with massive variance in scale and with massive variance in the basic characteristics of the data. We also routinely experience load spikes or unexpected ramp-ups that are not known ahead of time to the platform team. And so we're kind of finding ourselves playing this persistent game of whack-a-mole, where at any given point, it's very common that some data sets are severely behind or broken, and we're spending a lot of time just cleaning those up. In general, when we see a ramp-up in scale, we see a perfectly corresponding ramp-up in latency, and this almost always requires human intervention to resolve. And of course, this motivated us to ask the question, can we make tuning the computer's job? Of course, the answer is yes. I'd like to introduce Flink autoscaling, which is a feature of the Flink Kubernetes operator. At a very high level, I'll gloss over some details here. At a very high level, the way that Flink autoscaling works, you can define a target utilization in your Flink configuration, and it's now the Kubernetes operator's responsibility to tune the parallelism of your Flink app to meet that stated target. Walk through a couple examples now. These diagrams are from the open source autoscaler documentation, licensed through Apache. But in this specific example, we have our Flink application running just fine at our target 60% utilization. But suddenly and unexpectedly, we see this big ramp up in the input rate of our incoming data. As a result, our Flink app spikes all the way up to 100% utilization, and even still, it can't actually keep up with the scale of the incoming data. In response, the Flink Kubernetes operator will observe this situation, observe that utilization is higher than intended, and will scale parallelism to compensate, again, targeting specifically that 60% number that we chose originally. Conversely, there could be a case where our Flink application is running well under a certain amount of load, but as a result of a decrease in load, we actually find ourselves underutilized, which again is basically just wasted money. And in this case, of course, the Flink operator will notice that utilization is lower than intended and will actually reduce the parallelism to, again, target that 60% utilization number. And so we at OpenAI, we rolled out Flink autoscaling for all of our StreamLink Flink applications, and it was basically a resounding success. The overwhelming majority of our datasets are now able to keep up with their ongoing load with absolutely no hand tuning. We also saved about 50% of our CPU resources on the platform, specifically because we used to have many data sets that were over-provisioned. And nobody really had the time to go look at all of those data sets, but the computer has all the time in the world. It's able to identify those opportunities to save money. And now we're in a position where our load spikes typically self-heal without any operator intervention. OK, so I've talked a lot about the Flink Kubernetes operator and how it's a great solution if you want to deploy your Flink application. But what if you want to deploy 2,000 Flink applications? To answer that question, allow me to introduce the StreamLink watchdog, which I briefly mentioned on previous slide. The StreamLink watchdog is basically an orchestrator around the Flink Kubernetes operator that reacts to changes in configuration and in schemas for StreamLink itself, and creates, updates, or deletes Flink deployments in response to those changes. Walking through the architecture, again, we have our configuration files checked into our repo. These are deployed into production as Kubernetes config maps. And the StreamLink watchdog is continuously, repeatedly polling these config maps and also the schema registry for any changes that would either necessitate a change in configuration or just a restart of the application. The StreamLink watchdog, in turn, is responsible for creating, updating, or deleting Flink deployment CRDs, which are, in turn, picked up by the Kubernetes Flink operator, which manages the actual cluster and application lifecycle. So again, this is sort of a layer around the Flink deployment CRD. Another important tool in our arsenal when it comes to managing this massive fleet of applications is Retina. Retina is our one-stop shop for all things streaming at OpenAI. It's a place where our users can look at their Kafka topics, their Kafka consumers, their Flink applications, and most recently, their StreamLink datasets. And I'll show a brief screenshot of Retina. Basically, this is sort of a UI where both our users and our operators can get a holistic view of what StreamLink applications and datasets exist, how they're performing, whether they're healthy, and where the actual Flink UI can be found. Really, at this kind of scale, it's very hard to manage individual applications as pets. And so I highly recommend any use case where you have many, many Flink applications. I think this sort of automation is an extremely powerful tool. OK, so now we've got our system running in production, and we have the tools to monitor and operate it. But what's the user story here? How do our users actually get the data that they want in the data warehouse? I'll talk briefly about our configuration model. So historically at OpenAI, we've already built a fairly sophisticated topic-level control plane where our users can very easily create a new Kafka topic just by adding a few lines of configuration to a YAML file in our repo. For StreamLink, we actually extended this. We added an additional configuration block. Typically, this is 3 lines, sometimes more. But really, all you need to do as a user is spell out the name of the table into which you'd like to ingest your data. And from there, once your configuration change is merged, we actually auto-deploy that change, and we will pick that up in the StreamLink watchdog, typically within a few minutes of merge. And you as a user will have the data in your hands, able to be queried in our data warehouse within typically 15 to 20 minutes. And this is all 100% self-service, which is a very important design principle at this scale. So yeah, now we have this bright, shiny new platform, and our users love it, and we're getting all sorts of new use cases on this new platform. But we do still have a problem, which is that like I mentioned earlier, we have about 2,000 streaming ingestion datasets that exist already, and we have a legacy platform with which we're really not happy. We don't want to support that platform long term, but we also don't want to leave our users out in the lurch by breaking their stuff or by ceasing to operate that platform on their behalf. And so yeah, how do we resolve this conundrum? And the solution that we came to at OpenAI is transparent migration. What I mean by transparent migration is that all of the existing workloads on our legacy platform must be moved to the new platform with no disruption in service, with no meaningful changes in behavior, and ideally without the users necessarily even noticing that anything has changed. And this goes back to our requirements that StreamLink must be compatible in terms of features, in terms of performance, in terms of data quality with the legacy system. So our general strategy for transparent migration on StreamLink, we started by onboarding all of our legacy datasets onto StreamLink, basically in shadow mode, right into a secondary table not actually used by any of our real users. Subsequently, we backfilled all historical data from our legacy platform datasets into the new StreamLink shadow datasets. We did comprehensive validation of the StreamLink datasets relative to the legacy. And finally, we drove a big cutover operation in which we quickly swapped these datasets such that our users were now reading from the StreamLink datasets. I'll walk through all of these steps in a bit more detail, starting firstly with the backfill. Again, we have a guarantee on StreamLink that the output tables have the exact same schema and data quality characteristics as the legacy datasets. And so our backfill operation is really quite simple. It's basically just reading all data from the old table and writing it out to the new table. One very minor detail here, we do want to make sure that we do not duplicate or lose data as part of that backfill process. And so to facilitate that, we have to carefully, we firstly have to onboard StreamLink, get it running well, let it run for some time, and then we can trigger our backfill operation with sort of an overlapping range of data, ensuring that we are backfilling all the way up to when StreamLink started, and in fact having some overlap. We also have to purge any overlapping partitions to prevent duplicate data over that specific time range. Moving on to validation. So again, because we have the exact same schemas and data quality characteristics between the two systems, we generally expect that at a row level, these two data sets will be perfectly identical. And we can validate this. We can validate this by basically reading both data sets, doing a big join by the primary key, which in our case is the Kafka cluster, the partition, and the offset, and then taking a hash of the remaining, like the real data values in the data set, and comparing that hash between the two systems. We can consider a few different categories of differences here. There could be missing rows, there could be extra rows, or there could be actual differences in the same row. In general, we expect, and this has mostly been true in practice, we expect that there will be absolutely no diffs for the vast majority of these data sets. In the rare cases where we did observe diffs, it was the responsibility of a human operator to go investigate, root cause, and fix whatever source of data drift. In most cases, like the diffs that we did observe were almost always due to like small errors in our user-defined transformations or like schema evolution, that general shape of thing. It was very rarely an actual fundamental issue with the platform. So we were kind of meeting our desired goal of perfect compatibility. Now I'll talk briefly about the actual cutover process. So again, our starting point here is that we'll run StreamLink in shadow mode for all of our legacy datasets. Once we have StreamLink running in shadow mode, we can temporarily pause both systems. Then we can do a very quick swap operation where the StreamLink table is swapped with the legacy table. Subsequently, we can actually resume both systems, but now with the StreamLink dataset effectively in the primary position, and with the legacy system running in shadow mode, writing to a shadow dataset. One of the big advantages of this specific approach is that we always retain the ability to continue validating StreamLink against the legacy dataset even after the cutover, and we also retain the ability to actually fall back to the legacy system in the event of a catastrophe. At no point did we actually have to do that, but it's nice that we had the option. Walking through this step by step, again, here we have as a starting point the legacy platform running in sort of primary mode with our users reading the legacy dataset, and StreamLink running in shadow mode, writing to a dataset not really used or visible to anybody. As the first step in the cutover process, we pause both systems. We subsequently do a big swap. We effectively rename the tables such that all of our downstream use cases are now pointing at the StreamLink dataset, not the legacy dataset. And having made that swap, we can turn both systems back on, again with StreamLink now in the primary position and the legacy platform now in the shadow position. One sort of quick note here, there is a very small amount of downtime effectively for our users when we actually do that swap of the tables. But in practice, it's typically less than 30 seconds for the overwhelming majority of use cases. And yeah, for the most part, we can think of that as being non-disruptive for our users. And so we drove this general workflow to great success. At this point, we've actually migrated basically all of our legacy datasets onto StreamLink. I think there's maybe 10 remaining today. And really, we've had basically zero disruption in service for our internal users, which was always a goal, and which was a really encouraging milestone for us to hit. OK, awesome. Now that I've talked a ton about what StreamLink looks like, I'd like to share what we wish we'd known when we embarked on this project and on this migration. So we have a few fun challenges. One thing I'll start with here is Kubernetes cluster maintenance. So as everybody knows, Kubernetes is really designed for cattle, not for pets. The expectation on Kubernetes is that at any moment, maybe you'll lose a small fraction of your pods, and that shouldn't be disruptive. And for most use cases, that assumption does hold. If you have like a stateless service on Kubernetes, you lose one pod, who cares? It'll come back. But for Flink, losing a single task manager can actually cause the whole application to crash and restart, which can be pretty disruptive. And in one specific troublesome edge case, we observed a rolling restart of our Kubernetes nodes, causing persistent downtime and breakages for our StreamLink applications. Walking through that example in a bit more detail, we have our Flink application. It's running great. We have task managers on several different Kubernetes nodes. But we start a rolling restart. And firstly, the node 1 restarts, bringing the Flink application down. Eventually, node 1 comes back. We're able to reschedule those task managers. The Flink application starts recovering. But before it recovers fully, we kill node 2, and the Flink app is down again. And we actually saw this play out for hours at a time in a way that effectively broke all of our Flink applications in a single cluster, which was very troublesome to us. So candidly, we haven't really found a fundamental solution to this shape of problem. The tactical fix that got us unstuck in our case was simply to increase the soak time between consecutive rolling restart operations in the context of that specific maintenance. But in general, I think this is a risk that I think everybody should be aware of when deploying in Kubernetes, and I encourage you to work with your local compute team or your cloud provider to actually work to find a non-disruptive strategy for cluster maintenance. Another fun one for us was general gaps on the Flink SQL and Flink table APIs. So setting some context here, Flink SQL and the Flink table API are basically ways of defining streaming applications using declarative SQL syntax or using a data frame-esque sort of API, and to manipulate schemaful or tabular data in streaming fashion. And this is in contrast to the lower level and more mature data stream API. So for us, the table API was a big simplification of a core implementation, especially when it came to our user-defined transformations. It was really a very powerful tool that made our core app a lot simpler. But it did actually have some really painful gaps. So for one thing, we have no control over Flink slot sharing groups in the Flink SQL and Flink table APIs. Without getting too detailed on this, a slot sharing group is basically a way of controlling how Flink allocates parallelism for different operators in your Flink application. In our specific case, the way this played out was that we were only able to get, and in this example, we have maybe 5 Kafka clusters, each with 100 partitions. Ideally, we'd have 500 units of parallelism, but due to the slot sharing group limitation, we only had 100. We only had the number of units of parallelism for 1 Kafka cluster. And that's a really troublesome pessimization when we think about our very largest data sets, which really need all 500 of those partitions. Relatedly, we have no support for operator UIDs in Flink SQL and the Flink Table API. So operator UIDs are basically a way of mapping state between two different deploys of the same application. And Flink really needs stable UIDs to ensure that you can basically like change your app and then deploy it and have it come back in the same state as before. And in the absence of explicit UIDs, we actually observed that adding and removing Kafka clusters would change the topology of our application in a way that completely broke our ability to deploy from our last Flink checkpoint. And this is again really troublesome because it effectively means we have to like throw out the entire application state and start from scratch. So ultimately, we at OpenAI, we chose to patch our internal Flink fork to make these features work. And this was possible for us for a couple reasons. For one thing, we had a tremendous amount of Flink expertise in-house already. We're already maintaining our own fork for other reasons. And also, StreamLink as an application is frankly very simple. And so it was possible for us to kind of hack around this in a pretty invasive way. But this may not be possible depending on the specific context in your organization and depending on what kind of workload you're running. So I strongly encourage folks to think carefully about these limitations before you build too heavily on Flink SQL. So wrapping up soon here, coming to a few specific key takeaways I'd like to leave you folks with at the end of the talk. So the basic lesson here, Flink really is a very powerful platform for building streaming ingestion pipelines. Overall, our experience with Flink has been very good. We really did meet all of our initial goals in terms of TCO, in terms of latency, and in terms of reducing the burden of our streaming ingestion on Kafka. And so I highly recommend considering Flink as you consider building these systems out in your own organizations. Moreover, the Flink Kubernetes operator is really a very impressive piece of software, and I believe that it actually has saved us many hundreds of engineering hours. And I highly recommend the Flink Kubernetes operator as a way of deploying your Flink applications, especially if you have Kubernetes expertise or if you're already running Kubernetes clusters in-house. It's a great fit. And more broadly, the last point I'd like to make is that transparent migrations are a really effective strategy for managing technical debt as you're building new systems and as you're making invasive changes to existing systems. In our experience, it's very, very hard to make this kind of large-scale change if you need to work with each individual use case or each individual user to actually make it happen. The best migration is the one where the users don't even know that it's happening. And so I highly recommend folks to bake that into the design process as they consider building out new systems in large organizations. And with that, I'd just like to thank you all so much for coming to my talk and open up the floor for any questions.
I can ask a question. So earlier you mentioned that the rolling restart of a pod is very disruptive for the Flink. Why in Kubernetes you can cordon the pod or node groups, so any future jobs will not be scheduled there. So you could like cordon the half of it and then do the upgrades on the cordoned one, so the node job is getting scheduled there, and that would be fine. Is that something that you guys entertain, or?
Yeah, that's a great point. I think that the same basic issue can still happen, though. Like when you actually cordon that pod, like you either have to evict any running task managers, or when you cordon the node, rather, you have to evict any running task managers, or you have to wait for those task managers to naturally churn as a function of like a deployment or something. And so I think that like there's sort of two problems there. Like either you still break your Flink app transiently, or potentially your maintenance is blocked indefinitely for those workloads to vacate the node naturally. And so I think that cordoning is like a useful tool in this situation, but I don't know that it fundamentally changes the situation. I think the same edge case can basically happen.
Absolutely. It's just kind of partition node groups in one
yeah.
state.
Yeah, that's very fair. Yeah, I think that in part, like, we had limited control, even our compute team had literally limited control over how this maintenance actually happened. And so I think it's like a bit of an artificial limitation in some ways, but it is something that can happen in practice, especially if you're using an off-the-shelf like cloud provider sort of AKS, or a Kubernetes cluster, rather.
So you guys are an AKS.
Don't tell anyone.
Okay.
Yeah, so question on how, in your ingestion, how do you maintain your schema?
How do I maintain our schema? So
like, because you mentioned it's self-serve, right? So for whoever is producing the data, how do you know in your Flink?
Yeah, that's a good question. So I didn't really talk about it in this talk. You can find other talks from OpenAI online probably, but we do have some fairly sophisticated abstractions on the producer side as well, where we sort of manage our users' Avro schemas on their behalf, and every time they publish to Kafka, they do so through a very lightweight abstraction that handles finding the appropriate schema for their data on their behalf. And so unless users are really like sidestepping our abstractions intentionally, we're always quite confident, okay, like the data flowing through this topic has this specific schema, and we know where to find it in the Confluent schema registry and also in our mono repo. Yeah.
Now that you guys have built this out, like what is your next foreseeable scaling blocker? Is it the number of the topic count, or is it in a scalability of a Kubernetes cluster, or maintainability of that, or what is it?
That's a tough one. I would say I don't think we feel all that much pain on the streaming ingestion side from that perspective, just because it's a relatively simple workload, and like the operation of pulling a record from Kafka, serializing it as Parquet, it's actually not that heavy. So we don't feel that pain on this specific aspect of the platform. In general, though, like if we look at the growth curve of our overall Kafka throughput, we see like it's currently at 60 gigabytes a second. It was not that high in January of this year, for instance. It was an order of magnitude lower. And so we're sort of, one of the challenges here is how large can any one Kafka cluster get, and how quickly and easily can we create and integrate new Kafka clusters. So those are areas of active exploration on the team where we're just trying to figure out how can we add more resources to this overall system as quickly as possible, as non-disruptively as possible.
I'll be happy to talk to you about that later.
I know.
All right, if nobody else, thank you so much for your time.